And my name is Yannick Fratantonio. I'm a PhD student at UC Santa Barbara. And the work I'm going to present is joint work with my dear colleague Antonio Bianchi and Will Robertson and Engin Kirde from Northeastern University, and my advisors Chris Krugel and Giovanni Vigna. So as the title suggests, it's going to be a talk about detecting logic bombs in Android apps. And before starting with the actual work we did, I want to start with an example. So let's consider a normal application like Google Maps. And the user can select where he wants to go, and he gets the direction. And the user is super happy. Unfortunately, there is a functionality like the following in the app. Basically, after December 22nd, an attack is going to be performed on the app, and I don't know, the phone is going to be rooted, and your content is going to be leaked, and together with your embarrassing pictures. So in a logic bomb, the attack is not as malicious, it's more subtle. It's more related maybe to the logic of the application, and it's very, very difficult to detect. In this case, for example, it could be that the route that the user chose is not the shortest one, maybe it's the longer one, and you're going through different points. Now, for maybe a normal user, it's not that bad, but if you think this app might be used by a soldier in a military zone, you can see how it can be problematic. Now, let me generalize a bit. We call logic bomb a functionality that subtly modifies the program output, and it is triggered only under certain narrow circumstances. Okay? So logic bombs detection is very difficult because the attack is actually subtle. So existing approaches have been focusing on finding and identifying malicious behavior, but again, in this kind of logic bomb, the threat model is so generic, and the malicious functionality can be so generic that it's very, very difficult to encode what malicious is. So for this reason, we chose a different approach. Instead of focusing on the behavior, as all the other tools, we actually focus on the check. Why do we do this? But think about this for a second. Even if we don't know what subtle attack does, something happens only after December 22nd. Isn't that weird? So we took this observation, and we made it our key idea for this work. Basically, we want to focus on triggers and not on the trigger behavior. So in this work, we propose to identify logic bombs by using trigger analysis, which is a technique we developed for this paper, and that's what I'm going to present today. Trigger analysis is a static program analysis technique that aims to identify triggers. The input to the analysis is a Delvik bytecode of the Android app. The output is a list of suspicious triggers and the trigger behavior. And this output can be checked by a human, and so you can bet, hey, this is OK or not. The analysis is constituted by 4 main analysis steps. Of course, I'm going to give you an overview today. There are many, many details in the paper, so you're welcome to check that out. And I'm going to simulate what the analysis would do by analyzing the simple example I showed in the previous slide. So the input, as I said, is David bytecode. Something ugly like this. Don't bother reading it. What I want to point out is that a suspicious check looks like this. It's just an if bytecode instruction, and it doesn't tell us much, right? It depends on what the value in V2 is. Is it a normal check? Is it a suspicious one? We have no idea. That's why the first step of the analysis is symbolic execution. We do forward symbolic execution, and as of now, we track objects related to time, location, and SMS. We also, of course, need to handle strings and handle specific objects, such as intents and bundles. And we create a symbolic value whenever a relevant object is created or accessed for the first time. And basically, while the analysis goes through, we record all operations that are executed on this object. Okay? Basically, in this case, we have this if bytecode instruction. The analysis would tell us, well, V2 actually contains the return value of a comparison between 2 dates. And the first date is the current one. The second one is December 22nd. In this way, we are kind of getting what we call expression trees related to objects stored in these registers. And this, I will show later, is very important to be able to distinguish normal check against suspicious ones. Now, the second part of the analysis is what we call predicate extraction. So while we do the forward execution, we record was the condition, what we call block predicate, was the condition for a block to be executed, assuming that the analysis reached its predecessor. What we want to find is the full predicate for a basic block to be executed, assuming the analysis reached the starting point of the method. To explain this step, it's better to use an example. Now, let's assume this is the control flow graph of a simple method. Let's assume we have from B0 to B1 predicate Q. And then let's assume B1 introduces a check maybe related to time. And we identify the check as P. If P is satisfied, you go to B2. Otherwise, you go to B3. Now, to compute the path predicate, what we do is a backward traversal of the control flow graph, starting for each basic block. For example, from B2, we know that we need to satisfy Q and P. So while going backward, we managed to track, to reach to B2 starting from B0, we need to satisfy P and Q. Similar for B3, the condition would be not P and Q. We do this for each basic block. So for B4 and B5, what we would do is, well, to arrive to B4, we can arrive either from B2 or to B3. So the formula would be P and Q or not P and Q, right? So as you can notice, the formula for B4 and B5 actually depends on P. But if you check the control flow graph, no matter what P value is, B4 and B5 is going to be reached. So there is a false dependency. To eliminate this false dependency, we apply standard Boolean logic formulas, and we simplify so that the false dependencies are removed. The next step is what we call predicate characterizations. Once we have all these predicates, we want to understand how suspicious they are. So for this work, we adopted the following policy. We consider suspicious any ordering comparison between symbolic, time, and constant, bound checks on locations, and matching constants values against SMS body or sender. So for example, in the previous case, the analysis would assess the expression tree associated to this path predicate. It's an expression tree like this, and we say, wow, this is pretty suspicious. And so we flag it. Now, the next step is what we call control dependency analysis. We want to understand if these suspicious predicates are actually controlling the execution of something sensitive or not. Now, in this paper, since we focus on the triggers and not on the trigger behavior, we are able to adopt a very lenient definition of sensitiveness. So we cannot, it's not that we consider sensitive as functionality like sending SMS, but also internet connections, file system analysis. So a very, very lenient definition of sensitiveness. And what we do is a forward traversal of the super control flow graph, starting from each of these suspicious predicates, and we check if they are controlling the execution of something sensitive or not. And this step is interprocedural. So we propagate predicates through field definitions and objects and so forth. The last step of the analysis is what we call post-filter steps. It turns out, we found during our empirical study, that there are some checks that match our definition of suspiciousness, but they're clearly benign. So two of these cases are null checks. In the code, you will see an object compared to 0. These match our definition, but we know it's totally OK, so we can filter it out. Another interesting case we found is that developers insert checks like, is this field already set with a valid timestamp? So it turns out that developers put field equal -1 to identify not valid timestamp, and then later on in the code, they want to see if the timestamp was valid or not, and so they actually introduce a check, is this different than -1? Again, since -1 or 0 are not valid timestamps, we know it's not actually a malicious check, and so we can filter it out. Now, this is the overview of the analysis. We wanted to evaluate it, and we want to answer two main questions. Is the tool fast enough to analyze real-world apps? The second question is, can we find interesting stuff without raising too many false positives? So we collected two data sets. The first one is about 22,000 benign apps collected by a previous crawl of the Play Store. And we scanned these applications for APIs related to time, location, and SMS, and that's how we constituted these three smaller data sets. For the malicious apps, we collected 11 malicious apps written by DARPA red teams. DARPA red teams are organizations that were asked to develop next-generation malicious applications that were able to evade current analysis systems. And we considered 3 real-world malware samples that were relevant to our analysis. So for the benign ones, we ran this analysis with a 1-hour timeout, and the analysis terminated for more than 80% applications in all these 3 data sets, so it seems to scale reasonably. And for those ones that terminated, basically each step of our analysis was able to filter out many apps. Well, at the very end of this, basically we reduced to only 35 apps flagged as suspicious. Now, since these apps are from the benign data set, we consider these apps flagged as suspicious as false positive. But since we started with 10,000 apps, and now we have only 35, the false positive rate is very low. Nonetheless, the triggers we found in these applications proved to be very interesting. I'm going to give you an overview and some interesting samples now. So time-related checks, we found several checks for license expiration. So there are many developers that put an hard-coded date within the app, and when this check is satisfied, then some functionality of the app is disabled. And we found apps that want to implement schedule events, so something is run every day at 8 p.m. And we found functionality related to pseudo-random number generator implemented through time. Another application we found was containing a check against latitude and longitude. So it was comparing the current location with these hard-coded constants. And then when this was satisfied, a Japanese text is written. Of course, I have no idea what it means. According to Google Translate, it means welcome to Yamagata Station. And since we did not trust it, we actually checked, and it seems to make sense. Another app we found was My Remote Phone, again from the Play Store. It's an app that let the user locate their phone through SMS. The tool was able to identify this suspicious check. Basically, something happens when the body of the SMS contains MPS: and GPS. And we actually installed this application. We launched an SMS. We sent an SMS satisfying this condition, and we got back the exact GPS coordinates of the app. There was no authentication. And OK, in this case, I think it was more a vulnerability and not like a backdoor. But of course, in a malicious scenario, this could be an actual backdoor. More interesting, we found remote lock application. It's an application that let the user lock the phone with the user-selected password. And the tool identifies something like this. It's a body equals to a very, very long string. And it turns out that if you send an SMS like this, the phone unlocks. Again, another vector. Again, this application was found on the Play Store. For what concerns the malicious application, again, we ran the tool on these 11 DARPA apps, and the tool was able to identify a trigger in all of them. And I want to point out that even if these apps were synthetic, so written by benign developers, they were actually pretty complex. For example, in one of them, there was a check that was implemented by storing the result of a complex predicate on time in a field called new site flag. And then this later on would be used in another method to select, oh, maybe I should run the malicious application. Another application we analyzed was the hacking team's Android RCS. This application hit the news, I think, 6 months ago, because they found that it was used for like targeted attacks against activists, and it was extremely powerful. Basically, it was able to leak victims' private conversation and GPS location, track the device, capture screenshot, and so forth. And it turns out this functionality was enabled through SMS, and the tool identified a check like this, where basically each incoming SMS would check against a list of hard-coded strings or commands, and in that case, the application will abort the propagation of the SMS through the main application of the device, and it would trigger the malicious functionality. Now, up to this point, I hope I convinced you this tool is actually pretty nice, and you can find interesting triggers in these apps. Of course, we do have some limitations. The first one is that we can only support, as of now, a subset of potential trigger sources. As I said, we support time, location, and SMS related, but there are many other ways to implement a trigger. For example, environment-related triggers and stuff like this. And we are currently working on trying to extend this, but the current prototype doesn't support these other sources. Of course, there is imprecision and scalability of the static analysis. For our work, we were not running main issues, mainly because we found out that this time, location, and SMS functionality are implemented in a very localized way. And so this made the analysis, of course, simpler. But maybe if you try to send this tool to other kind of trigger sources, you might run into issues. Another limitation is that an application could move the trigger outside the app, for example, a network backend. But even in this case, I argue that the app would still need to contain a trigger. Because if you send something on a network, the network decides for you, the network still needs to send to the application, do something or not. So the app still needs to contain a check. Maybe it's a network-based check, and of course, it's much more difficult to detect, but something is still there, so I think there is still hope. And of course, we have issues with obfuscation. We work on David bytecode, and we cannot support analysis of native code, reflection, and dynamic code loading at this point. OK, let me conclude. We developed trigger analysis, and we propose to use it to identify logic bombs in Android apps. And it turns out that if you run this tool on benign apps, there are not many false positives, so we think it's an interesting approach. And I want to point out the key idea of this work is to focus on triggers and not on a trigger behavior That's what distinguishes us from all the previous analysis tools. And I think it would be really nice if this work would inspire more analysis techniques to actually try to characterize better the conditions that are controlling what actually happens on our phones. With this, I thank you all very much, and I'm happy to take any questions.
Jaehyun Jung, Microsoft Research. Really nice work. So I've been also recently looking at those kind of trigger behaviors, and I've seen many cases that apps collect so many external kind of triggering information, like the kind of system variables and so on. And then after it collects all those things and then sort of do other checks and then invoke this trigger behavior. Do you think your analysis can catch that? So that's question number one. And then number two is, I understand that native code is out of scope, but I've also seen a lot of cases that the check happens in the native code, and then trigger behavior sort of happens in the Java side. So how would you sort of deal with that?
So for the second question about native code, I think the idea would work also for binary. Of course, it's much, much more difficult to implement. And I think it's much easier for the attacker to obfuscate things. But we believe this kind of like hard-coded checks or this kind of triggers will be used mainly for, I don't know, target attacks. And I mean, maybe for applications that are submitted to the App Store of the Department of Defense. And maybe in those cases, obfuscation and maybe usage of native code can be already ground for rejection. So it's difficult. Idea, I think it might work, but it's difficult. But maybe in some scenarios where maybe this subtle logic-related malicious functionality are actually used, maybe this native code usage might be already a flag for them, and so they would take. For the first question, as far as I understood, you said there are these apps that collect this information from different sources, and then they do something.
Right.
But the check is on what? I mean, there is the collection.
Right, check is on the collection, and then sort of the, combination.
Oh, I see. So basically a combination.
Right.
Oh, I see. Oh, interesting. In that case, okay, as of now, of course, we don't tend to this. We focus only on this time, location, SMS. Isn't it weird that something happens depending on combination of some sources? What I'm saying is that maybe you can write an analysis that says, collect all these sources, and then there is a check depending on all these possible things, then it might be suspicious. Of course, to understand if this approach is reasonable, you need to have a large-scale analysis, try on many apps, and see if you raise too many false positives. Okay. But if it doesn't do it, then it might be a solution.
Stelios Sidiroglu, MIT. Really like this work. I just want to ask you, if you were to defeat your static analysis, what would you do? It seems like you're tracking directly objects right now. I mean, how is your analysis object sensitive? And how does the information flow? How would you defeat your static analysis with what you know?
The simple trick is what I pointed out in the limitation. Maybe you put the trigger somewhere else. And again, as I said, you might have the trigger from the network, but there are issues in the sense that network-related functionality, you have many more cases that would fit our definition of being suspicious, because maybe you have protocol parsers and things like this. And so I think as of now, this will cause problems for our analysis.
What if you pull things out from the object that you're currently tracking? So you're taking things through intents and binder, and sort of you're tagging the object, right? What if you pull information from the object out? Would you be able to track that?
Yes. So we rely on API's annotation, and we took some other annotation from previous tools. What we do, we have a selection of like APIs we support. So for example, if you have time object, then you can do get month, get date. Then we say, hey, this is actually a month of something. And for intents and strings, we have a limited support, but we do have some supports where you can say store something in an intent, and now we know this intent intended with this information. Of course, we don't know maybe the super precise value of what's inside, but we know, hey, this intent contains the month and the day of the current time. So.
Okay, I think I understand. Okay, thanks so much.
Absolutely.
All right, last question. We're running out of time.
Great talk. This is Don from Qualcomm. So quick question for this is, you mentioned you did like inter-procedure analysis for triggers for predicate stuff. So how often do you see the source function, the sync function, and the predicates or locally happen in a very small call graph or happen interprocedurally?
That's a good question. So I know for the apps I manually analyzed, so for the 35 apps that my tool identified, I checked them all manually, and it was very localized. I think in 2 cases, there was something where there was you store the result of a check in a field, and then later on, this field is actually used. For the DARPA apps, it was it happened more often because they actively try to trick us to not detect things. But that's an interesting question. I don't know the answer. I think the best way would be to actually do an experiment and see how complicated these functionality are, depending on the type of sources you're using, time, location, or whatever. I don't know.
I see. Then for interprocedure analysis here, do you handle, like when you have virtual function, do you do the very conservative analysis, or how do you handle that actually?
You mean virtual functions?
Yeah.
Oh, yeah. So in bytecode is much simpler than in binaries. So basically, you have an invocation. You know the signature of the method. So you just need to analyze the class hierarchy, and you have a small number of targets. So even if you don't track constraints super precisely, you can get away with it without having crazy explosions of states or imprecisions. So, yes.
Thank you. It's a great talk.